Oh, sorry. Okay, yeah. No one is not. Okay, yeah. All right. So if you, yeah. So if you were like me, like 18 months ago, like looking at JWST launching just after Christmas and wondering, like, will it want it, and it did not blow up. So it actually went very fine. It kind of did all the maneuvers as better than expected. So that means hopefully we'll have a nice telescope to work with, looking to the high redshift universe for a very long time. And so in Michele's absence, I'm just going to talk about a little bit about what JWST has been doing in the high redshift universe, and trying to see where the next things might be coming up. So with JWST, we do know that, is that a clicker? Like, is there a light on this? Oh yeah, okay, yeah. So we expect JWST to start looking into the dark ages. So maybe if we're lucky in the next few years, we might see the first stars and the first galaxies for sure popping up. So it'll be quite interesting to see what comes up with this data. To go back in time, since the first data came out 12 months ago or so, I think the best way to address what has happened is to go back to cycle 0 and start at the very beginning. So there were 2 large programs in terms of extragalactic science, which looked into the high redshift universe. One was the GLASS JWST program, where Michele, I, and Carl, and there was a few ASTRO members who were part of. And then there's the CIRRUS program, which also looked into one of the Hubble, Hubble deep fields, one of the legacy fields. Both programs used a technique where you observe the first round to find interesting targets, and then in the second round you go and do spectroscopic follow-up. So it's kind of a neat way to find new candidates that we did not know about before JWST came online. So this is just a ground-based image around the Abell 2744 cluster, just to wow you with one of the images before I get into the science. And this is what we saw before. And then for GLASS, we observed in the H and K band in this small part here. I don't know, the screen is, because of the lights, I think it's really hard to see. So, but once you did do JWST imaging, you can see the quality of the data that came out is really cool. And you see structures that you did not see before. You're going to see a lot of lensing things. And afterwards, with cycle 1 tertiary programs like Uncover, we have been able to look into the depths of the cosmos, especially with a lot of aided by gravitational lensing. We are seeing so many structures we did not see before, looking from globular clusters to high redshift AGN quasars. Like, all of these things are popping up. But most of this data was public immediately. So if you were like me, if you about 1 year ago, everyone was working frantically to get the data out to be the first, because there are so much small egos in the high redshift community. So the quality was kind of not that great, I would say, in the very beginning, because we found a lot of Redshift 20 candidates and stuff, which has been slowly being rolled out. But in some cases, it did work out fine. For example, in these cases where you have a larger break in the around the Lyman break, even though the NIRCam mid filter 0 points were not well understood, that break meant there was a little bit of leeway to play around with. So because of that, we managed to find good candidates that we did not see before with Hubble, especially with these ERS programs. So things were looking good. And I think from now on, I will try to focus on the advancements we have made with JWST in the past few months. So to start off with, let's go back to the era before we had JWST. So the high redshift universe looked something like this. We had a lot of redshift 6 or so. We had about redshift 6 or so Lyman alpha galaxies. So we had an imprint of the reionization era. But once you go into redshift 8 and above, the number of sources significantly dropped. This was purely because of observational reasons. But within 1 year of observations, not even in 1 year actually, like, we have completely transformed our view of the very early universe. We have now galaxy candidates going up to about redshift 16 or so. And you can see the transformation. The highlighted region is a region that we had no candidates before. So you can see we're getting like dozens of sources, and some of these things are actually spectroscopically confirmed as well. So we're opening up this new window into the very, very early stages of the reionization with JWST. And to start talking about spectroscopy, I think the best candidate to do this is to go back into the first source, the most high redshift source we knew before the JWST era. That's called GNZ11. And thanks to wide field camera GRISM, we had an understanding of what this redshift should be for this source. We knew there was a galaxy around redshift 11. It was very, very bright. And this is the best quality spectra with 12-orbit Hubble program could give us. And here you can see there is a small black blob coming up. And then if you collapse it and do some SED fitting, you can clearly see there is a break. And this break is because of like Lyman break, basically. So it's absorbed by the, anything below that is absorbed by the intergalactic medium at these redshifts. And with JWST, now we have transformed this by this galaxy so much that within a few hours of exposure, you can actually see a whole window opening up in regions that we did not see before. We see so much emission lines popping up, and you can zoom in further with high resolution. And you can see these emission lines are actually not single component ones. You can have to fit multiple components to see how they're getting broadened up with different AGN and other effects. So we are going from just confirming these galaxies by just using photometry or these breaks into actually studying the ISM and gas properties at redshift 10, 12, etc. So we are kind of transforming what we saw. And also, that was just one example. We have now candidates confirmed with spectroscopy up to redshift 13. These are a few heavily binned examples. The quality varies, but we actually now try to see the Lyman breaks, and we can confirm that these galaxies do exist. So science-wise, the main thing that we want to address is how does reionization, how did reionization happen, right? We need to understand what kind of galaxies were responsible for this. And to do that, we need to know what kind of, basically we need to have a histogram of UV luminosity in the early universe. So if we do this with HST Hubble ultra deep field data, we see around redshift 9 or so, which is similar to what we see with HST. But if we go into high redshifts, we see the slope might actually getting bigger. So in this example here, you can see if you compare between where the things cut the axis, you can see that the slope is getting bigger. That means there is more galaxies with higher UV luminosities, maybe at high redshift. Is this a problem? I think we don't know yet. This is the answer, because if you do the cosmic star formation rate density, this is the famous Madhav-Dickinson plot, which you might have seen before, and you plot down constant star formation history models here, you can clearly see at the higher redshifts, it seems to deviate slightly. So we are kind of addressing one of the main goals of JWST, because we want to know in the early universe, did the star formation rate efficiency, for example, how efficient galaxies were converting gas into stars. Is it more efficient or less efficient in the early universe? And the indications are there is some deviation, but we don't know whether what is causing this, because it could be like change of the mass to light ratios as well. So there's a lot of work to be done. So we need more data and to understand the emission line properties, etc., do proper modeling. So it'll take some time, but I think within the first few months, as you can see, we have made progress on to start looking at that window. Apart from the brighter ones, the low luminous ones are also very important, because we know reionization was likely driven by low luminosity galaxies, because these are the ones that can actually, with stellar feedback and stuff, will have more opportunities for the Lyman continuum photons to escape through channels. So these are the ones that would likely ionize the universe. So this is one example of a galaxy we discovered around redshift 10 with the GLASS program. And it is about 1/20th of our Milky Way L star, basically. And it's half solar metallicity, and it's one of the very, very low luminous galaxies that we have observed in the early universe. I can plot it in the distribution here. And you can see if you look at the UV magnitude was a redshift, it's a significant outlier. And even for this very low luminous galaxy, within the short exposure time with the DDT program, you can clearly see there is some marginal emission lines coming up. So if we go in deeper, I think we'll be able to actually study the ISM properties of these sources in great detail. Coming back a bit closer to us, we also have started to find some early protoclusters to confirm some of these with spectroscopy now. So we know there are galaxies clusters forming in the early universe. And we can do some creative modeling to see what would end up at redshift 0. So it might end up with something like a coma-like cluster. So we are now probing around redshift 8 or so, what's the role of environment, and then how big are the ionized bubbles, and etc. So it's kind of opening up a new window. And one of the most interesting things about JWST is that it's finding a lot of these AGN-like sources. So for the emission line, if you work out emission line ratios, do BPT diagrams and other things, you figure out that most of these sources do require fall into regions where ionization has to happen from anything apart from star formation, which means that there can be a lot of AGN activity going on in these galaxies. And in some of these sources, we have even found, like there's marginal detection in X-ray as well at redshift 10. So there could be a lot of black hole activity happening in the early universe. And I think this is one of the growth areas in the high redshift universe, because when we know how the early black hole seeds grow, that gives us an idea how star formation is being regulated in the early universe. And we can look into Eddington and super Eddington growth ratios and try to see, like, are the galaxies that we are finding with JWST, are they nominal galaxies at the redshift, or actually breaking the models or going towards the high end? So there's a lot of degeneracies at the moment. And I think this is definitely a space to watch. And connected to that is that when you work out how much massive systems there are in the early universe, when you compare with what we knew with HST, the JWST is finding so many massive sources in the early universe. There are significant degeneracies between AGN, dust models, etc. when you do SED fitting, but it's kind of pointing towards there is a lot of AGN in the early universe, quasars that we did not know, which means there was a lot of dust, for example, in the universe, and we completely missed this population in the early universe in the HST era. So I think it'll be one of the key findings in JWST in the future to constrain these number densities. We're also finding a lot of quiescent galaxies in the early universe, redshift 3 to 5, and most of these galaxies do have AGN features, and similar to what Monse's trailer showed, this could actually mean that this AGN is responsible for quenching these high redshift sources to be early massive quiescent systems. And apart from that, we are finding a lot of momentarily quenched galaxies at redshift 7, 8 era. So this might come back to the thing that Darren was talking about earlier, like finding these very, very older systems, but might have been quenched for a shorter time. So to finish off, I'll quickly say what might happen in cycle 2, like 2 of Australian programs have got more than 1,000 hours to look into the high redshift universe, doing imaging over 600 hours in NIRCam, and also doing H and K band spectroscopy as well. So there will be like tens of thousands of galaxy spectroscopy happening by programs led by Australians. And of course, Tanya, who's in Astro 3D, also got like IFU program to look at the IMF. So there will be a lot of nice data coming along. And with these massive data sets, we will be able to look into the high redshift universe in detail. So put your thinking caps on. We will do another masterclass probably in Sydney. We probably get some money from the space agency to do that. So like, if you want help with the cycle 3 proposals, we are happy to help during towards the end of the year. And we're also organizing a JWST IAU symposium at the Cape Town General Assembly. So keep an eye for that as well. I'll send some emails around later on. I'll let up here. And this is the list of things I did not talk about because it's hard to put everything in it.
Congratulations. It's amazing.